This is very simplified illustration of the 5G beamforming. Unlike broad 4G antenna radiation, the 5G beam is focusing on you. 5G will use massive MIMO antennas that have very large number of antennas element or connections to send and receive more data simultaneously. The benefit to users is that more people can simultaneously connect to the network and maintain high throughput. Beam steering is a technology that allows the massive MIMO base station antennas to direct to the radio signal to the users and device rather than in all directions. This increases efficiency as it reduces interference. Then, how to beam steering and beam switching? An antenna can employ radiating element with a common frequency to steer a single beam in a specific direction. Different frequency beam can also be steered in different directions to serve different users. The directional signal is sent to is and calculated dynamically by the base station as the endpoint moves, effectively tracking the users. If a beam cannot track a user, the endpoint may switch to a different beam. This granular degree of tracking is made possible by the fact that 5G base station must be significantly closer to users than previous generation of mobile infrastructure. Beam steering is achieved by changing the phase of the input signal on a radiation element. Phase shifting allows the signal to be targeted at a specific receiver. This engineering slide might be very difficult to understand in short time, so just remember the major key parameters which control the beamforming. Pi is how much phase shifted between two element signal, and zeta is overall beam steering angle. At the far-field modeling, time delay matches the time difference of the wavefront striking each element. Time delay can also be emulated with a phase shift. In summary, each antenna element signal phase shift make beam moving. Cool down from head-edge massification, then let's study visualized phased array antenna beam with MATLAB experiment. All experiment images are absolutely not copied and pasted from the others, developed all by myself. Primary object of this MATLAB experiment is to show real phased array antenna beam in our recognition of the world. Seeing is believing. No need to study MATLAB, just enjoy the show. There are two types of phased array antenna. One is consists of a 4-element linear array antenna, and the other one is consists of 16-element linear array antenna. They are linearly arranged in 3D dimension. Target frequency is f to 28 GHz, and arrow direction means 0° reference pole side beam direction. The bulky 3D polygon means real 3D world electromagnetic beam of the linear array antenna. The most bulky one is main lobe beam, and adjacent wings are side lobe beams. Instantly, you can compare the shape between 4-element array and 16-element array antenna. 16-element array shows more narrow beam width. Narrow beam width means more accurate beam. If the number of array elements increases, then beam width is reduced. This is a 2D projected polar and Cartesian beam plot. We can estimate the beam strength with this view. HPPW, half power beam width, is an angular width which the signal power is half of its peak value, easily 3 dB beam width. This basic comparison of both types array is set to 0° beam steering. This means that beam is directly straight out from array plane. 16 array shows small, narrow half-hour beam width, which energy focused more accurate beam. Then now our beam is steered to 30 degrees from the center. Check out the changed beam shaping in each direction in 3D view. Likewise, 30 degree steered beam in project view. The center peak of the main beam is pointing 30 degree direction. If we compare this 30 degree result to 0 degree, we can figure out that main beam width is become wider than 0 degree. As the beam degree is away from the reference bore side, then beam width is widened. Try more radical beam angle to 75 degree. Obviously, we can see there is a strange great lobes appear. That on inside lobes are the result of a spatial aliasing. We hate these extra radicide lobes. There is no free lunch in the universe. Pi and theta and element distance is restricted in design. In restricted design parameters, rating side lobes are inevitable. Fortunately, we have a workaround solution called tapering to remove annoying side lobes. Abrupt edge uniform energy distribution of array make spatial sink function radiation. By changing the energy weight of array which have smooth edge, side lobes beam level is decreases. However, still there is no free lunch. With applying tapering technique, main beam width is increased as a side effect. Let's see more interesting 16 by 16 uniform rectangular array. This is basically similar to linear array, and as we already recognized, this has two-dimensional azimuth and elevation angle steering control. Two-dimensional arrays shows more accurate narrow beam width, focused beam targeting to user. Rectangular 2D array also got same problem of side lobes when larger array angle beam steering. Likewise, tapering technique can also apply to the rectangular array to remove side lobes. With applying tapering technique, main beam width is increased as side effect. Angular resolution requires a narrow beam. A narrow beam requires many elements. On actual implementation, accurate beam width need more phase control bits. Not enough phase control bits make quantization error, which affect side lobes level.